What's good, guys? In this video we're going to cover dynamic memory allocation, more specifically the malloc function and the calloc function. So why don't we get started with malloc. So what's dynamic memory allocation and why am I learning it until now? Well, before this video, if you haven't used malloc or calloc, the way that you've been creating variables is being managed by your computer, meaning that your computer reserves it at the beginning of when you create the variable and destroys that variable at the end of the program. This is just typically by using integers, right, floats, structures, the whole like. All of these videos, all the variables that I've been using have been on the stack. So in a nutshell, it means the stack is memory that your computer handles for you. It handles the allocation of variables and deletes them for you, right? When you put things on the stack, the computer just takes care of everything for you. You don't have to worry about it. But there are some drawbacks. Because the computer's looking after it for you, kind of small, relatively small, right? You can reserve a lot of data on the stack, but if you need something absolutely gigantic, it'll be pretty tough for your computer to handle that for you while being fast. So there's this unused area of memory, which relative to the stack is even larger, called the heap. And that's kind of like the Wild West. Your computer doesn't really touch that area. However, it's reserved for you to manage it if you'd like to. And one way of going about managing that memory is to reserve data in that memory. Like when you create an int or a float or a double, normally your computer will reserve, the 1 byte, the 4 bytes, the 8 bytes in the stack for you. But here, by using malloc, we are going to be reserving the data for us. So how do we start about using dynamic memory allocation and reserving memory from the stack? Well, it starts with a pointer. I'm going to create a pointer called floaty, and it points to a float. So what I'll do here is that first I'm going to cast the returning data type of this function as a pointer to a float, because malloc returns a void pointer, and I'm going to call malloc for memory allocation. So how does this work? Well, I need to provide the size of memory that I want to allocate in bytes, but a float is 4 bytes, so I can put 4 here and I should be fine. But this is kind of not so user friendly. There is a better way of doing it, and it's by using the size of function. You may have used it for determining the size of arrays. Here we're using it just to get the size of a float. So we know that this is 4 bytes. But here we can definitely tell that we are only getting the size of one floating point value. So with that, we have just allocated memory on the heap. But because we are doing it on the heap, because we are allocating the memory on the heap, well, we're managing this memory now. So we are responsible for floaty. And sometimes it can feel like a bit much. So once you reserve data, the next thing that you should do is to make sure that you free it, that you get rid of it. Once we are done using these 4 bytes, we need to make sure that the reservation is finished, so that way other programs in the computer can use this memory when the program is done. So I can go about that by calling free. So malloc allows us to reserve data on the heap, and free lets us get rid of it, so that way other resources of our computer can use those 4 bytes. And it's just 4 bytes. It doesn't seem too much, but typically here you want to reserve a whole ton of data on the heap. Usually reserving large groups of data is done by using the heap. So it's very important, so that way you free that memory, so that way it can be used. So the next thing that I'll do is that I'll have floaty, and I'll give it a value. Then, I can treat it as if it was any sort of pointer, any other, pointer that's been used. And I can dereference floaty to get its value there. So we compile malloc, a.out, right? We're able to use it just as some pointer to a floating point value, right? But now instead of having the computer manage all the memory behind it, we are the ones managing that. So not only can we do this with floats, we can really do it with any other data type that we have. Let's have a character for example. I'm going to cast it as a pointer to a character. We're going to do malloc, and you know what? I want a string of 7 characters. So I'm going to use 7 times size of character. Now, if you don't know, the size of a character is just 1 byte. So putting 7 here is enough to fulfill what the function needs. But just putting a number is not easily readable. But however, doing something like 7 times the size of a character, this is easier to see that, oh hey, we're reserving 7 characters. So why don't I go about populating string? And here we are. I have very cleverly populated string with the string floaty. But there's a problem here. I forgot to free the data for string. It's quite easy to go and reserve memory, but freeing that memory is always easily forgettable. And I'll be honest with you, I do it myself. But my general rule for using malloc and reserving dynamic memory is as soon as you call malloc, as soon as you're done writing the code to call malloc, you go to the bottom of your program or the end of the scope where the variable that's being dynamically allocated is done, and you free it. For these examples, I'm putting them at the bottom of the program, but if I really wanted to, I can free floaty right up here. Right, the thing is, if I free floaty on line 8, if I try to use floaty as if it were a variable, I would get a segmentation fault, because once I free the data there, right, it's no longer going to contain data. So if I try to access it or treat it like a normal pointer, I will cause a segmentation fault. So if that's not, well, this is not what I want to do. I kind of want to play it safe, just in case I want to do stuff with floaty, in the future. Maybe after I do something with string, I can change the value or something. So I'm putting it at the end of the program. Right in for string, doing the same thing. This is kind of just a habit of what I like to do. So why don't we go about running this code? Okay, not bad. This behaves as one would expect. It behaves as if I have just normally created a string. Right, the only difference between is now, instead of it all being in the stack, because I'm calling malloc, I'm putting it in the heap, and I am directly managing the memory for these variables. So sometimes your programs get very, very complicated, and it's very difficult to see if you have missed putting a free somewhere where you needed to, right? And if you don't put free and you leave memory that's recorded or reserved, allocated or reserved, right? If your memory is allocated or reserved on the heap and you don't let go of it, it's stuck there. It's stuck there. It's not overwritten by other programs. It's a terrible way of filling up the memory that you have with data that's no longer being used. And when that happens, it's called a memory leak, right? Your program's running, you allocate a certain amount of bytes, and when it's done running, you free some of it, but not all of it gets free. That's a memory leak. Ideally, and what you guys should strive for to do, is that the data that you allocate at the start of the program or throughout the program should be deallocated at the end of it. So, what can we do to detect memory errors? Well, there's a nice program called valgrind, and you can use, if you're on Ubuntu, you can install valgrind this way. Right, so I didn't have it installed in this computer, so I can show. Oops, excuse me. So I can show the download for this, and it's going, and it's done. So now that valgrind is done downloading, if I want to use it to check for memory leakage, I do val grind. I'm going to do dash dash leak dash check equals yes, and I compiled it, right? No, I need to compile it. A.out. And well, this is the result. I need to update. Well, actually, I don't need to update because I didn't add any new code to it. But here I've just run it. So I do valgrind. I do the leak check equals yes, and then I have the name of my executable as the third argument. So I'll do memory checking. It'll say, okay, this is the command. Here's my program, and it gives me a heap summary. So it tells us total heap usage: 3 allocs, 3 frees. Right, this is how many bytes were allocated. All heap blocks were freed. No leaks are possible. So that's pretty good. But let's go here and let's comment this out. Let's make a mistake. Oops. Because I was so enthusiastic about doing dynamic memory allocation, I forgot to free the data. So I'm going to compile it. And now if I run valgrind, it'll run it for me. Uh-oh. The data that's used at the exit, 7 bytes, makes sense because the character's 1 byte, and since I allocated 7 of them, there's 7 bytes. There are 3 allocs, 2 frees. So it tells us 7 bytes are definitely lost by using malloc in our function main. Here in this example, because it's so simple, it's able to break down which function caused the error, which dynamic memory allocation call allocated the memory and where it was done, right? But that's not always the case. Sometimes your programs are so complicated that it might not be able to give you all this. But it gives us a leak summary that 7 bytes were definitely lost. So I know here that, I have a problem with my dynamic memory allocation. In the next video, we're going to cover 2 other functions. So now we cover 2 here, malloc and free. Right, malloc is used to reserve data, free is used to unreserve it. But now in the next video we'll cover calloc and we'll cover realloc. I'll see you there.